guys, we are back for another lecture. Today we're going to be covering series parallel circuits, and as you can see, I've already got the circuit drawn out. This one's a little bit longer, just kind of like they were with the capacitors. There's lots of stuff to find. We do have to do an additional step this time. We have to find the individual impedances of each of the inductors because we do have to take into account their winding resistance for each of those. So for that, everything else is going to be the same on how we find these guys. We just have one extra step that we have to go through and solve for the total impedance of these devices. And so what we're going to do is we're going to go through again solving these equations. I am going to do one small change compared to what I've been doing earlier. And you guys will see that when we get down to solving the impedance for the parallel branch. As I talked about in the last video, we have a couple of different means that we can use to solve for the impedance. Previously, we've been using the reciprocal method, where we take the reciprocal of the reciprocals added together for all the different components, and that is one way to do it. In this one, I'm going to do it where, since we just have two branches, I'm going to use the product over the sum. So when we go through that, that's the method I'm going to use. You can still use both methods, but I wanted to make sure you guys can see that yes, even what we learned, last semester with these different methods is still applicable. So with that being said, let's go ahead and get right into this. I'm going to try and color code this a little bit better for this one so you guys can kind of see the different parts and see where everything's broken up. Hopefully I can stick to this. If not, it is what it is. I'll do the best I can. So to start out with, we have our generator. It's sitting at 6 volts peak with a 50 kilohertz signal going into it. Connected to that, we have point A, which is connected to R1, which is 6.8 kilo ohms. Connected in series to L1, which is 27 millihenries, and has a winding resistance of 80 ohms. Now we get into our parallel network, and the first branch, which is B, we have R2 is 2 kilo ohms, and that's connected in series with L2, which is 110 millihenries, and 230 ohms of winding resistance. And then our final parallel branch, which is branch C, has R3 in series with L3. R3 is 1.1 kilo ohms, and L3 is 130 millihenries with 197 ohms of winding resistance. Okay, so let's just get started into this guy. So the first thing we want to find is the reactance values for each of our inductors. So remember, to find the reactance of an inductor, it's equal to 2 pi times the frequency times the inductance. So the reactance for inductor 1 is 2 pi times our frequency, which is 50 kilohertz, times our inductance, which is 27 millihenries. So when we solve that, that comes out to be 8482 at an angle of 90 degrees, and that's in ohms. To find the inductance, the inductive reactance of inductor 2 is 2 pi times our 50 kilohertz times our 110 millihenries, and that gives us 34,558 at 90. Then we want to find the inductive reactance for inductor 3. So again, it's the 2 pi times our 50 kilohertz times 130 millihenries, and that gives us 4841 at 90 degrees. So real quick, we just got to plug into our calculator, get the formulas, and again, the formula that we have is up there. Okay, so we're going to switch to the next part where we're going to solve for our impedances for all these different components. Okay, so the first step we need to find is the total impedance of inductor 1. So remember, we're going to be adding these guys together. So we take the winding resistance plus the reactance value, and that's going to give us into rectangular notation, and then we're going to convert it over into polar. So we have 80 ohms of winding resistance plus J of 8482. Because remember, our reactance is imaginary. We can't physically measure it. It's just the byproduct of running a frequency through it. We're going to convert that into polar. That turns into 8482 at an angle of 89.46. Now, if you do look at these, one thing to kind of take note is, yes, this 80 ohms is negligible against this thing. The only thing it's doing is changing the phase angle just very slightly. And honestly, we probably would never see this kind of shift on a scope unless we zoomed in really, really far. But because we're trying to be as accurate as we can, we want to take it into account. There will be times in the future where we will assume, where this 80, it's not going to have any effect on it for all intents and purposes, and we can just leave it as our XFL value. But for now, we want to make sure we include it and we account for it, because like I said, when we get later, this isn't going to make much of a difference later in life. But I want you guys to understand how these things are and how they work. So now, the next part is we're going to solve for the impedance for inductor 2. And again, we use the same formula. We have 230 ohms of winding resistance plus our J of 34,558. So that's the total impedance in rectangular. We want to convert this into polar. So we got 34, make that a little bit better, 34,559. So in this case, it did affect it by 1 ohm. And we have an 89.619 degree phase shift. So now we're going to find the total impedance for inductor 3, where we have 197 ohms of winding resistance, and our reactance value is 4841. We're going to convert that into polar, and we end up with 4841 at an angle of 89.724. Now, one of the things to note too is the winding resistance we can't just ignore. It all depends on what our frequency is. So if we were running these inductors at a lower frequency, say something like 5 kilohertz, so 10 times less, we would see these values drop by 10 times. So for example, L1, if we were running it at a lower frequency at 5 kilohertz, we would see about 8,400 ohms. Which now that 80 is still not quite significant, but if you look at the other guys, so if we drop down to 3,400 instead of 34,000, we have the 230. That's a little bit bigger chunk. We're going to start seeing a little bit more drift. So the winding resistance does come into part when the X of C, X of L values, the inductive reactance values, are smaller. So when they start getting larger and larger, this is something too that we can take into account, that no longer that's not going to affect our circuit much. We're still going to get a little bit of drops throughout, but they're going to be insignificant. Okay, so now that we have those impedances, now we need to come back. We need to find all of the impedances for these circuits. So we have the section here for A and B because we're going to add these guys together to find our total impedance. So A to B, we're going to find the impedance of R1 and L1. The impedance from B is going to be R2 and L2, and the impedance of C is going to be R3, L3. And then we're going to combine branches B and C together to get our parallel, and then with that we're going to add that into our AB impedance, which is R1, L1. That way we can get everything together to get our total impedance to solve for the rest of the circuit. So, like I said before, the impedance from A to B is equal to R1 plus ZL1. So that comes out to be 6.8K plus J of 0. That's our R value in rectangular because it has no reactive component to it. Plus our 80 plus J of 8482. So that's the total reactance or impedance that we found for L1, which we just found earlier in its rectangular form. And we're going to need them in both, so at least on these impedances, it's easy to go back and forth and just have both in rectangular and polar notation as we keep going. So we end up with our impedance for A to B is equal to 6880 plus J of 8482. Now we can convert that guy into polar notation because we're going to be doing some math with it. But again, we're going to want it in both these forms. So at least for the impedances, like I said, always do your impedances in polar and rectangular. It'll just make your life a little bit easier. And then when you go to the rest of the components, when it gets to current and voltage, it kind of just depends on how you're going to be using them on which form they are. Generally, you're going to be needing them in polar, but sometimes you're going to need them in rectangular, and you can kind of see which ones you need as you go. So when we convert this guy, our impedance for A to B is equal to 10 921 at an angle of 50.953 degrees. So there's that value. Here is these ones. Most of the time on the quizzes and on the homework, they're going to want the answers in in polar notation anyway. So just kind of as a word, use polar notation as default, and then if needed, use rectangular. All right, so now that we have our ZAB, we need to find the next impedance. So the impedance for branch B, and remember our subscript notation, if there's nothing there, it goes to ground. So that is going to be R2 plus the impedance of L2. So we have our 2K plus J of 0, and that's going to be added to our 230 plus J of 34,558. So ZB comes out to be 2230 plus J of 34,558. Remember, all we're doing is we're just combining like terms. Real values added to real values, imaginary values added to imaginary values. We're going to convert that guy to polar, and our final impedance for ZB comes out to be 34,630 at an angle of 86.308 degrees. Now the last one we need to solve for is the impedance of branch C, and that is going to be R3 plus the impedance of inductor 3. So we end up with 1100 plus J of 0. That is going to be added to 197 plus a J of 4841. ZC ends up being 1297 plus 4841. Going to convert that guy to polar, and ZC is equal to 4862 at an angle of 88.181 degrees. Okay, now that we have those, now we can solve for the rest of these guys. So this is where that switch is going to happen like I was telling you about. So instead of just using the reciprocal method where we would take these guys, and I'll show this real quick. So our Z parallel total, usually we're going to go through and we're going to use this method of ZB plus 1 over ZC. This one will work every single time. Right now we're just going to use one of the special cases. So we're going to take this guy, and we're not going to use him. We're going to use one of our special cases. So remember, way back when we were talking about resistors and things in parallel, that we also have this method. So our Z parallel total, we can also find by having our impedance of B multiplied by the impedance of C over the Z impedance of B plus the impedance of C. So we have the product over the sum rule. That's still another option that we have to solve for parallel circuits. And you can use either one of these. But the only restriction on this guy is you can only use it with 2 branches. So if you have 3, you could do this twice, or you could just go back and use the reciprocal method and do all 3 of them at the same time. So with that, we're going to use this method on this problem just to show you guys that we'll still get the right answers. Okay? So when we look at it, when we're looking at our equation, we have a multiplication on top. Great. We have everything we need in polar notation. We can multiply it that way. Okay? Well, now we're adding things, so we need in rectangular. So that's why I was saying it was a good thing to have these guys in rectangular notation to start with, because we're going to add the rectangular values together. One caveat too is if you have the rectangular values, you can multiply together a rectangular value by a rectangular value. You just have to go through and FOIL it. Do your first values, your inner values, your outer values, your last values. You're going to end up with an I squared. I squared is equal to -1. So you're going to have one value that's going to be a negative value, or it's going to be the opposite polarity of whatever it was. And then you just have to remember to subtract that value through, but you'll end up with a final value in rectangular form that you can use. But again, then we're going to be dividing, so they need to be in polar anyway. So it's just kind of a good idea in practice to at least have your impedances in both rectangular and polar form as you go. All right, so let's get into solving this guy. So the Z parallel total is ZB times ZC over the impedance of B plus the impedance of C. So what does that look like when we spit it out? Well, the first thing we want to do is we want to add together our ZB and our ZC. Kind of do that first, get that answer, and then get that converted into polar so that we can come back and do this division later once we get that multiplication done. So we're going to do this part first. Then we're going to do this part second. And then we're going to do the division third. All right, so ZB plus ZC. Well, we go back and we look at their rectangular values. So for ZB, we had 2230 plus J of 34,558. That was added to the impedance of C, which was 1297 plus J of 40841. So now again, we have our J values, our real values. Oops, there should only be one. And so we want to be able to add the like terms together. So when we do that, we end up with 3527 plus J of 75,399. And now, like I said, we come back up and we're going to be dividing, this number is going to be our divisor. So we need to convert this guy into polar. So when we convert him into polar, we end up with a 75,481 at an angle of 87.322. So there's our first value that we need. So now we come back and we look, okay, we got our first value, now let's do our second value. So now we need to take our impedance of branch B multiplied by impedance of branch C. So that's going to be, 34,630 at an angle of 86.308 multiplied by 40862 at an angle of 88.184. So that value is going to come out to be, when we carry it all through, so ZB times ZC is equal to, now remember when we're doing this, I'm just using this as a placeholder for our original formula. That's going to be equal to 1.415 gig at an angle of 174.492. Okay, so now that we have that value and we have this value, now we can go through and do our third. So this is our first calculation, this is our second calculation, and now we need to do our third calculation. So we take the 1.415 gig, which is 10 to the 9th, at an angle of 174.492. We divide that by this value we got from our first equation, by the 75,481 at an angle of 87,322. So we divide those together. The 1.415 gig divides by the 75,481. And that gives us 18,746 at an angle of 87.62. So this right here is our Z parallel total. So a little bit easier because it only involves one real conversion. And the only conversion we have was right here on our first equation. After we added them together in rectangular, we converted that answer into polar. Now everything's in polar, we can just divide it out. So for this instance, when you have two parallel branches, it makes life a lot easier because you don't have to convert back and forth. But you do have to remember it's product over the sum, and you have to have both the rectangular and polar forms of each of the values. But like I said, less conversions, less errors, or less times for mistakes. I know that's kind of one of the biggest things is converting back and forth between polar and rectangular. Feel free to use whichever method you would like, does not matter. Like I said, it just kind of depends on your preference. So there we have our final impedance total for the parallel branch. So now the last thing we need to do is we need to take our Z total that we need to find. So in this case, it's going to be the Z from A to B plus our impedance for our parallel total. So this guy we're going to have to convert back into rectangular to be able to add them together. So when we do and we convert that guy into rectangular, we get 778.463 plus J of 18,730. So now when we come back down here, our Z total is going to be equal to the 6880, which is the value we got from AB, plus J of 8482, plus this value we just solved for, the 778.463, plus J of 18,730. Now again, we're going to add like terms together. And our Z total comes out to be, in rectangular notation, is 7658 plus J of 27212. We're going to convert that to polar because we're going to need to divide this value. So we end up with 28,269 at an angle of 74.282 degrees. So there's the total impedance of the circuit. That's everything combined together is going to provide 28,269 ohms of resistance, impedance essentially, opposition to the AC current for the entire circuit. So now that we have those values, now let's go ahead and continue on and solve for the next parts. So after we have our impedance total, we can calculate how much current we have flowing through the circuit. So the amount of current we have flowing through the circuit is equal to the voltage total divided by the impedance total. So we start out, and if we go back and look, we have 6 volts that we're starting with. So we'll come back down, we have 6 volts peak at 0 degrees, and our impedance total is 28,269 at 74.282. We run that through our calculator. I total comes out to be 212.247 microamps at an angle of negative 74.282 degrees. Now that we have those, now we're going to continue on using that value. We're going to solve for the voltage drops across R1 and L1, and then get our voltage drop across VB, so that way we can continue on and find those currents through the individual branches and find their individual voltages. So now we take VR1, the current going through it is I total, multiplied by resistance 1. So we got 212.247 microamps at an angle of negative 74.282, and that is multiplied by apologize, my pen just froze for a minute. That's multiplied by 6.8K at 0 degrees. So VR1 comes out to be 1.443 volts, and this is peak voltage, at an angle of negative 74.282 degrees. So that means when we hook this guy up to the scope and we measure him out, we use the math functions, all those different things, we're going to end up with a value of 1.43 volts at this angle. So it's going to be, almost 90 degrees behind what the signal, the reference is, our input coming in. And the inductors are going to have the voltage is going to be way in front. So it's just the opposite that we would see with the capacitors. The inductors are going to lead the resistors. So now that we have VR1, we can find the inductor 1's voltage. So again, the current going through it is I total and times the impedance of L1. So the whole thing, the winding resistance, the X of L, everything. So we end up with 212.247 microamps at an angle of negative 74.282 degrees. And that is multiplied by our impedance for L1, which is 8482 at an angle of 89.46 degrees. So VL1 comes out to be 1.8 volts at an angle of 15.178 degrees. And then the last part we need to solve for is the voltage across B, from B to ground, which is our parallel network, which is our I total times the impedance of our parallel branches. Because remember, when we combine those together, we reduce it down to a single series value that we can then use to solve for these guys. So we have 212.247 microamps at an angle of negative 74.282 degrees. And the impedance for our parallel network was 18,746 at an angle of 87.62 degrees. The voltage across this guy comes out to be 3.979 volts peak at an angle of 13.338 degrees. Okay, now that we've gone through all this work, we want to make sure that what we're doing is correct, and make sure that what we did up here is still valid and we didn't screw anything up. And the problem is this is about the first chance that we get to kind of determine what is, if we did this correct or not. So we're going to go through now, we're going to solve for our KVL. We're going to look at the voltage drop of this loop right here to make sure everything comes out to be 0. So remember that we start, it doesn't matter where we start, we go around in the loop, and all the voltage sources and all the voltage drops have to equal 0. So to kind of simplify and streamline that process, we know that according to that, so the voltage source has to equal all these voltage drops. So it has to be VR1 plus VL1 plus VB. Those have to equal each other. Otherwise, we've done something wrong and we're dropping voltage in places that we shouldn't. So here's our formula for our KVL. So the Kirchhoff's voltage law double check. Make sure that we have these voltages correct. So now we just start writing these out. So our voltage source was 6 volts at 0 degrees. VR1 was 1.443 at an angle of negative 74.282. Our voltage across the inductor was 1.8 volts at an angle of 15.178. And the voltage for our parallel network was 3.979 volts at an angle of 13.338. So now, if these guys were all the same angle, we could just simply add them together, but they're not. So the way that we have to add is we have to go through and convert all these guys into rectangular notation. So after we do that, we end up with 6 plus j of 0 is equal to 390.913 milli plus minus j of 1.389. The next one becomes 1.737 plus j of 471.274 milli. And the last one becomes 3.872 plus j of 917.936 milli. So now we just kind of want to double check real quick in our heads, make sure these make sense. So we have here, our first one has an angle of negative 74 degrees, which means that's going to be very highly towards the reactive side of the scale. towards the imaginary side. So we should see the imaginary value should be a lot larger than our real value, which it is. So that at least follows our trend. The next one, we have an angle of 15 degrees. So that means it's approaching 0, which means our real value is going to be larger. So in this instance, yes, it is larger. And here it's about the same, so we should still see the similar kind of breakdowns of how they're going to split. So at least we know that we're going the right direction. We just still have to verify that we have all the right answers. So now again, we're going to go through and we're going to add all the like terms together. So all the imaginary terms are going to be added or subtracted together depending on what they are, as well as all the real values are going to be combined together. So when we do that, we end up with a total of 6 plus j of 0 is equal to 6.000, and the reason I'm putting those is because that's what my calculator spit out. After doing all that math and everything, it came out to be exact with that. And then we have a minus j, and the reason this next part, I didn't give it a prefix or anything, a metric prefix on there, to break it up, is I just wanted to kind of show how, what this number actually is, milli, micros, that kind of thing. So what we ended up with was 2.16 micro, or 216 micro, I apologize. So compared with a 6, or a 0 compared to a micro, I wanted to break this out just to kind of show it out. So we ended up with a 0.000216. So when we're comparing these two numbers, our 6's matched, so we're good there. And then our imaginary numbers, we are, let's see, tens, hundreds, thousands, 10,000s, 100,000s, millions. So we're 216 millionths away from being on the correct answer, which in this part is very, very insignificant. So we may not have come up with exactly the numbers, but for all intents and purposes, these numbers are the same. And even if we were to take this and round it off to our normal 3 digits that we usually do, that's where it would split up. So the 216 would fall off and we'd end up with 0. So even just with our rounding, we would end up to get the same. So these two values, they are the same for all intents and purposes. So which is good, which means we can continue. We didn't screw anything up. And the reason why we do that double check is just so we can have this little sanity check to make sure that what we're doing is correct. We don't always have to do this once we get comfortable with doing these steps. I still like to do them every once in a while just to make sure I didn't fat finger anything on my calculator, or I didn't write anything down weird or anything like that. So anyway, so with that, now that we have those values, we can continue on. So the next part that we need to find is our current through branch B and through branch C, since we know that our voltage drops are all correct, at least according to Kirchhoff. And usually if Kirchhoff is agreeing, then we've done something correct and we've done everything else right. So our IB is going to be equal to the voltage of B, which is the voltage of our parallel network, divided by the impedance of branch B. So we have 3.979 volts at an angle of 13.338 degrees, and divided by our impedance, which is 34,630, at an angle of 86.308 degrees. Our current comes out to be 114.9 microamps at an angle of negative 72.97. So that is the current we have flowing through branch B. The current we have flowing through branch C is equal to the voltage of the parallel, that's why we can just use VB because they are the same voltage, divided by the impedance of branch C. So we have 3.979 at an angle of 13.338, and the cool thing is with that voltage right there, we could hook the circuit up, hook the scope up, and we would measure that angle drop across both parallel branches. And that's going to be divided by 40,862 at an angle of 88.181 degrees. IC, the current through branch C comes up to be 97.377 microamps at an angle of negative 74.843 amps. Okay, now that we got those two currents, now we want to do one final double check to make sure we didn't fat finger anything there. So we're going to do a Kirchhoff's current law check. So remember that Kirchhoff's current law simply states that the current going into a node has to equal the current going out of the node. So if we come back up here and look at our main circuit, we have our I total coming in through here, and then it splits when it hits point B, and now it breaks into two currents. So this is our IB and our IC. And then when they come back together, they reform together to get us our I total. So when we come back down to our working area, if I can get my screen to scroll, we want to prove that I total is equal to the current flowing through branch B plus the current flowing through branch C. So we'll put these values in and then we'll solve them down. So our I total was 212.247 microamps at an angle of negative 74.282 degrees. That is equal to 114.9 micro at negative 72.97 plus our current through branch C, which was 97.377 micro at an angle of negative 74.843 degrees. Now again, we're adding these values together, so we have to convert them all into rectangular notation. So when we do, we end up with a 57,498 micro minus J of a 204.310 micro is equal to a 33.651 micro minus J of 109.862 micro. So there's our current through B in rectangular. And the current through branch C comes out to be 25.461 micro minus J of 93.99 micro. So there's our values converted into rectangular notation. So again, we're going to add like terms. So the reals will combine, the imaginaries will combine. And we end up with 57.498 micro minus J of 204.31 micro. So that is our total. And we end up with 59.112 micro minus J of 203.852 micro. So now when we're comparing these guys, the one things we want to look at is each of the values. Are they close enough? And then kind of overall, is the thing close enough? In this instance, I can tell you that yes, we are fine and these are going to be close enough. And the reason why we have some of these discrepancies is, remember back when we were solving for our impedance total, the value that we got there, we rounded off quite a bit because we went from the values I'll show you, come back up here and look, is right here in our third equation. When we went through and we solved for these guys, I cut this off at 1.415 gig. There was another 6 digits after that I could have included, which would have pulled this value a little bit closer, which would then have pulled everything else closer. So remember that how you round things off is going to affect things down the line. Now with this, like I said, this is going to be close enough. 57 microamps versus 59 micro in the real, that's close enough. That's within our 5% easily. The 204.3 micro versus 203.4 8, that's definitely well within it. The only question I would have would maybe the 59 to the 57, but we're still only 2 microamps different compared to, to 55 or 57, for example. 10% is 5.7. 5% is 5.35 microamps. So we're still within the 5%. We're probably sitting about 3-4%. But just know that that's where those discrepancies can come from. So with these, they are close enough. We are close enough. We are less than our 5% tolerance, so we can continue. And we can continue with confidence that we have the right answers. Okay, so then the next parts we have to do is we need to solve for the voltage drops across the last 4 of our components. So the voltage drop across R2 is equal to the current in branch B times R2. So we have 114.9 microamps at an angle of negative 72.97 multiplied by the 2000 ohms at 0. So the voltage drop across R2 comes up to be 229.8 millivolts at an angle of negative 72.97 degrees. Then we want to find the voltage drop across inductor 2, which is the current of branch B times the impedance total of inductor 2. So 114.9 microamps at an angle of negative 72.97 degrees multiplied by the 34,559 at an angle of 89.619 degrees. We run that through our calculator. The voltage drop across inductor 2 is 3.971 volts at an angle of 16.649 degrees. Now, on this next, after we're done with those, if we wanted to, we could double check again these values using Kirchhoff's current law. So if we wanted to, we could double check these guys, like I said, with Kirchhoff's voltage law, sorry, not current law, the voltage law, to where the voltage drop across B, branch B, is equal to VR2 plus VL2. But I'm not going to worry about that for 2 reasons. One, we've already proven that that voltage is correct based on Kirchhoff. And everything else we've done has been fine, has been correct, and we're doing the exact same things as far as the steps go. And then also we just found that we just used Kirchhoff to prove that our current was correct. So our voltage and our current are correct going into the system. So the only where I could have fudged is fat figuring something into my calculators. But like I said, I feel confident that because of those 2 conditions are met, that these values are going to be good, because this is just simple Ohm's law at this point. We're not doing anything fancy with it. We're not doing any tricks, nothing else. It's just Ohm's law. And I'm confident in Ohm's law. So we're not going to worry about this right now, but you can double check if you so desire. So now that we have those, the last 2 we need to find is the voltage drop across R3. And so that is the current of branch C times R3's value. So we have 97.377 microamps at an angle of negative 74.843 multiplied by 1100 at 0. So voltage drop across R3 comes out to be 107.115 millivolts at an angle of negative 74.843 degrees. And then the last step we have is find the voltage drop across inductor 3. So again, it's its current, which is the branch current of C, multiplied by the impedance total of inductor 3. So we have 97. Make this a little bit nicer. So we have 97.377 micro at an angle of negative 74.843. That is multiplied by 40841 at an angle of 89.724. So the voltage drop across inductor 3 comes out to be 3.977 at an angle of 14.881 degrees. And with that, we have solved everything. And I think I did actually stick to my color codes on this one, so yay for me on that one. But like I said, that's how we go through it. With the rest of these steps, like I said, we did the exact same as what we did before with the capacitors. We just have to make sure we keep track of what is what, keep everything in the same order as much as possible. And the only difference that I did on this one was we did the product over the sum rule because we only had 2 branches versus doing the reciprocal rule. Now, if you wanted to, we could go back through, or you can go back through and you can go through the reciprocal rule, and you should end up with something that's pretty dang close within a couple of points of this value that we calculated here, if not the exact same. It just all depends on the rounding that you do on your calculator. This one I feel we didn't have much rounding because we didn't convert much. We just used the values that were already given. For me, this one is a little bit easier because, like I said, there's only one case of where you have to convert versus the other one, like I said, where you're constantly converting back and forth between polar and rectangular and back and forth and back and forth. So either way you want to use is fine. And let me just double check. Yep, and I think we got all the components too. So that's the end of that. That is a series parallel RL circuit. With that, this video is already going at 45 minutes, so we're going to just do the one example today. And then my next video I'm going to have is going to be transformers. We're going to talk about some of their theory of operation, how they work, how to record them, what their schematics look like, things like that. And when we're done with that, that will conclude the material for this week. As always, if you have questions, please reach out to me. You guys have my phone number, my email address. And once again, please reach out if you do have questions. That's what I'm here for, is to help you guys out. So enjoy and do good.